Hello everybody, my name is Desiree and today I'll be taking you through the Quiz-Kit Hello World tutorial that you would have completed already on the CodeDrills platform. Okay, so let's get started. So this tutorial, as I mentioned, is a Hello World, so basically it's an introduction to Quiz-Kit and a bit of an introduction to quantum computing as well. At the end of this tutorial is a sample problem, which hopefully you have had an attempt at solving yourself, and I will be going through the solution for that. So as Radha had mentioned in a previous introductory video, there is a notebook that you can find at this link here, which will take you to a screen that looks like this, where you can actually run some code. You will not have to install Quiz-Kit or any other packages. You can just import it straight away here, and you will be able to test out your code and really get a hands-on into the tutorial. So let's continue. So Qiskit is an open source software development kit. So it allows you to work with quantum computers, allowing you to create your own circuits, have control over pulses, and develop algorithms. So we have simulators and real quantum computers available that you can use. In this tutorial and in the contest, you will only be using simulators, but if you are interested in running your code on real devices, then I'll give a bit more information about that later on. So classical computers are your everyday computers, and they take information in two values, just 0 or 1. So these are called bits. Quantum computers actually aren't just limited to 0 or 1 like classical bits. You can have an infinite range of states, anything in between these two. So this is called superposition. So in order to use quantum computers, we create quantum circuits. So these are computational routines which consist of coherent quantum operations, so qubits, and you can apply quantum operations to these qubits on the quantum circuits. So the operations that you apply are called quantum gates. So there are a set of common gates which all have a similar classical equivalent. So for example, the Pauli X, Pauli Y, and Pauli Z gates. So the Pauli X gate you might have been familiar with in a classical sense. That's called the common NOT gate. So just a flip operation. So here are some links for more resources into more introduction to quantum computing. So have a read of this before continuing if you haven't already. So this will give you an introduction into the common gates. And in the second link here, you can see how the gates affect qubits. So how they actually affect something called the block sphere. So you can learn about it here, and all the math behind it, if you're interested, is in this resource as well. So let's get started now. So your first quantum program. Firstly, but we need to import Qiskit. So the relevant packages that we will be using here, the relevant libraries are the quantum register, classical register, and quantum circuit from the Qiskit library. So let's just copy that over to our notepad here. So we can just import that here first. Next, we want to define our quantum register and our classical register. So here you can see that our quantum register takes in a value of 1, and so does our classical register. So what this is doing is it's creating one quantum register and one classical register. So basically, one qubit is being defined here. So let's copy that over as well. And then finally, to define our quantum circuit, we can pass in the quantum register and the classical register. So this is basically creating a quantum circuit with one qubit and one classical bit. Okay. Now, in order to run a program on this notepad, all you need to do is click run. So now you see I have clicked run, but nothing is being output here. That's because we haven't printed anything or there's no output expected. So it's working perfectly so far. We know we have no errors in our code. Let's continue. So let me introduce you to single qubit gates. So these are operations that act only on a single qubit of the quantum circuit. So as I mentioned before, some gates have a classical equivalent. So the Pauli X gate, which I mentioned, performs a bit flip to the operation. So applying the X gate to a 0 state when you measure it, it will actually be measured as a 1 now. Some single qubit gates have no classical equivalent as they take advantage of quantum properties. So an example of this is the Hadamard gate. So this is a fundamental quantum gate, and it utilizes properties such as superposition of a state. When you apply the Hadamard gate to a qubit, it actually results in an equal combination of the 0 and 1 states. So let's have a go at applying the Hadamard gate to the circuit. It's as simple as just going QC, so our quantum circuit that we defined earlier, dot H. And then we need to define which qubit we actually want to apply it to. So here we want to apply it to our quantum register, so our qubit. We want to apply it to the first one, so the 0 index here. Now, before executing our circuit on a simulator, we need to measure the states of the qubits. So when we measure it, we actually destroy the state of the superposition. So we need to, that allows it to collapse it down to either the classical 0 or 1 bit. In order to do this in Qiskit, it's as simple as running qc.measure. And here we are specifying that we want to measure the QR, so the quantum register, and collapse it down onto the classical register, CR, that we defined earlier. Okay, now let's visualize what we've done so far. And we can do that with qc.draw. Let's run that now. And you can see our circuit that we've created. So we have one quantum register, one classical register, and then we have added our Hadamard gate to the first quantum register, and then we've measured it. So we've measured the first quantum register and classed it onto the first classical register here. Perfect, exactly what we want. So as I mentioned before, circuits can be executed on real quantum computers or quantum simulators. And as I said, we're only going to be using simulators here. If you do want to have a go at coding on a real device, you can create an IBM Quantum account here. And then this will allow you to use this graphical interface here, a drag and drop program, if you want to create quantum circuits, and it will allow you to also have access to running on the real quantum devices as well. So this is a very useful tool, the Quantum Composer, which I mentioned before, this drag and drop here. This is an excellent way to get your hands dirty and see exactly how the quantum gates affect the circuits and the output measurements. So we will be using Qiskit Air to simulate the quantum circuits here, specifically State Vector Simulator, which returns a quantum state, a complex vector of 2 to the n dimensions, where n is the number of qubits. So let's just import this here. We can place this at the top with the other import statements, and then in this line here, we are defining our backend to be the Air simulator. Now we need to use the run function. So this helps us to compile and run the circuit. A job object will be returned that contains information about the job submitted to the backend. We also need to define the number of shots within this run function. So this is representative of the number of repetitions of each circuit. So usually we want a large number of shots in order to increase the sampling. This is because of the random nature in quantum devices. So usually this is set to 1024 by default. So let's copy that over. Perfect. And then once you run a program, a job object is created that contains the method job.result. So this returns information such as the raw data, histogram data, and state vector for your experiment. When you run result.getCounts, it will show us the histogram data for your experiment, which you can see here. So once again, we need to import something from Qiskit. So what this is just the visualization tool, so it allows us to print out a histogram. Let's import this up here. And Then here we have our job.result. So that is what I just mentioned. And then from result, we need to get the counts. And then the counts can be used to create the histogram. So let's run that and see what the results are. Perfect. So as expected, we have a histogram with two states, 0 and 1, with approximately equal output. So that is exactly what we expected for a single qubit circuit where we applied the Hadamard gate, because as I mentioned, the Hadamard gate has creates an equal probability of measuring the 0 and 1 state, and that's what we see here, approximately equal measurements of both. Okay, now that we have gone through all that knowledge, let's put it to the test with this sample problem. Let's go through the steps quickly. First, we need to create a quantum circuit with 2 qubits. Then we need to apply the Hadamard gate to each of these qubits. Then we can return the quantum circuit and click submit to submit the answer for grading. So you can see down here, this is the template that we have, and we can fill in our code before submitting it. So as I mentioned earlier, Qiskit provides a notepad in this link here that we can actually test out our code and run it and make sure that everything is running smoothly without you having to download any of the Qiskit libraries yourself. So let's get started. So firstly, we need to create a quantum circuit with 2 qubits. Here we see that QC is already defined, so we need to specify the quantum circuit with quantum circuit, and then we need 2 qubits, so we can simply enter 2. This will generate a quantum circuit with 2 qubits and 2 classical registers for us. Now let's move on to step 2. We need to apply a Hadamard gate to each of these qubits. So in order to apply a Hadamard gate, we do the same thing as I mentioned earlier. We go qc.h, so that applies a Hadamard gate to the circuit. Now we need to specify exactly which qubit to apply the Hadamard gate to. So Python indexing starts at 0, so we need to apply it to the 0th qubit, which is the first qubit in this case. As we need to apply it to both the qubits, we then need to do it again. qc.h, and then apply it to the second qubit, 1. So now we can run it to see if we are correct. And this is exactly what we expect. So as I mentioned earlier, the Hadamard gate puts the state into an equal superposition. As we are applying it to 2 qubits, we now increase the number of states to 4 here, and each of them have a roughly equal expected outcome. So that's exactly what we expect. Let's see if we're correct. Perfect. Hopefully this introduction was helpful, and all the best for the final contest.